I wanted to speak to you tonight about how we've been using Scala in production. So Scala in play, like microservice architecture in production, what we've learned from actually using Scala, what worked and what was a bit more challenging. So my name is Pascal. I've written a book on using Scala in data science and the libraries, Scala libraries that are useful for data science, Spark and things like that. And I also maintain a little open source like plugin for Jupyter Notebooks. This is a Python library for visualizing data on Google Maps. It keeps me entertained. It's good fun. I'm a data engineer at ASI Data Science. And maybe the most public facing aspect of ASI Data Science is that we run an 8-week fellowship where we take people with very strong quantitative quantitative backgrounds like PhDs or postdocs in physics or engineering or maths, and we give them just enough knowledge of data science and of a real world to be productive members of a data science team. And as part of the 8-week fellowships, the fellows do a 6-week project where they are embedded in a company and try and tackle like a real data science problem that that company is facing, and at the end try and deliver like a real artifact, like a program or a dashboard or whatever that actually hopefully adds value to the company. And we also run a data science consultancy that focuses on actually making delivering working programs rather than just slide decks. And so as part of the engineering team, we work on supporting both of these activities. And so we found by running a lot of this sort of short to medium term engagements that a lot of the engineering work up front was quite repeatable. So you'd start a new project for data scientists. Typically the first thing you have to do is you maybe create some like network hard drives and put the data files on them, create some databases in AWS, create some servers on EC2 which have data science libraries, whatever modelers like to use, hook up those servers to the right hard drive and to the right databases, make sure everything's secured, etc. All that's a bit of a drudge if you're an engineer, and so we set about automating some of this. And so we've been working on a platform for collaborative data science that we call Sherlock ML. So anyway, basically the point of my talk is what we've learned trying to build this platform in Scala. So imagine you have two data scientists working on two separate projects. So we have let's call the first one Angie and the second one Ben. And Angie and Ben are collaborating on one project, whereas Ben is working on the second one by himself. And if they're collaborating on one project, they basically have to share the ability to mutate the project state or to interact with the project state. They have to be able to access data files that have come in, databases, code artifacts, whatever. And so basically, in a nutshell, what Sherlock ML does is give them a nice interface for just creating virtual servers that are already connected to the right databases or whatever in the context of a project, and it's already secured. And by automating some of this, it makes it much less error prone. You're much less likely to leave a port open or a database unsecured or whatever and leak your client's data all over the internet, which is not something you want to do. Okay, so and the servers that we run offer basically a Python interface, because that's what the fellows and the consultants typically use. But despite it offering a Python interface, we've decided to build it as a suite of Scala microservices, Scala in Play. So how many people here have used the Play framework? How many people are generally familiar with the Play framework? So about 30%, okay. So, for those of you who don't know, the Play framework is basically just a web framework, and it's fairly convenient for writing HTTP, REST API type things. You can also write fully fledged web app that serve HTML, etc. But we mostly use it as a tool for building REST APIs. So in terms of the microservices that we have the core, obviously, authentication, authorization, and then a project service that keeps track of who's a member of what project. And then we have like a service for keeping track of secrets. So these are external secrets like database credentials or temporary keys for accessing AWS. And then we have a service that manages the creation of these ephemeral servers. And these servers are basically little Docker containers that come preloaded with Jupyter. And we run these Docker containers on Kubernetes. Kubernetes is a platform for orchestrating Docker containers that was released by Google. It just works, which is pretty good in the world of DevOps. So if anyone has Docker container orchestration, I very much recommend looking at Kubernetes. It's been super helpful. We then have a service for managing the creation of these hard drives that we need to hook up to projects, and that's backed by Amazon Elastic File System, which is a part of AWS. It's basically just NFS hard drives, but it offers a fairly nice API for creating these. And then we have the last major service is a service for managing the creation of relational databases that we can also attach to projects. And that's backed by Amazon RDS, which is Amazon's, like AWS's hosted relational database system, which also mostly works, which is great. And these services all like communicate with each other over HTTP, and then we have a node server serving a React front end so that the modelers can use a point-and-click interface to create their servers, which they like better than the command line, apparently. So what did we learn from actually building this and using Scala in production? So the first thing is, if you're in the microservice world, everything you do is always asynchronous, and there's very strong concurrency. You don't really know when a request is going to come in, etc. So you're basically stuck with concurrency, and concurrency is difficult. So Scala has great concurrency support natively, and then we use akka a lot for managing the state in a concurrent environment, and akka just offers a very, very nice abstraction in terms of actors, etc., for keeping track of the state. Otherwise, I'm sure many of you know keeping track of state in a concurrent system is a bit of a nightmare. The other thing that we've learned and appreciated, I think, as we've matured, is using types everywhere by putting as much information as possible into types. We've got much better at basically telling the compiler what we wanted the program to do, and so the compiler would tell us when the program didn't actually do what we intended. So, I guess to give an example, let's say we're writing a little authenticate method, and maybe a naive way of writing this is to pass in the user ID as a string and the password as a string, and maybe you return a Boolean. And that definitely works. The problem is you can get the two inverted, the user ID and the password the wrong way around, and the compiler has no way to know whether or not you're doing that right. So maybe a slightly better way, or a different way, which says a bit more overhead, is to wrap these in small value classes and pass those in. And you're basically telling the compiler exactly what you want to pass in. And so if you put in a password instead of a user ID, the compiler is going to tell you very quickly, which is great. The next thing is maybe your method froze, and so you could throw an unchecked exception, but if you're coming back to this code a couple of months down the line and using it, you might have forgotten that this throws an unchecked exception. By just wrapping the return value into a try, you're avoiding that problem. You're basically anyone using that method is forced to handle the exceptional flow. So yeah, like embedding information into the types is much better than having exceptions at runtime. The last thing that we have used a lot, which is nice, is maybe returning a Boolean or a try Boolean is not very expressive if you're using that, and so defining a little ADT, a little algebraic data type, to encode the result in the type system is a bit more definitely more declarative. So you can define like a sealed trait authentication result that you return, and then you return a subclass of that type. So we define basically the different outcomes here of what the authenticate method returns. And so if you're calling this authenticate method, it's much easier to understand for someone reading the code what's going on if they see, case invalid user goes to returning like a 403 or whatever, rather than just case false going to returning a 403. And since we're using a sealed trait, the compiler can tell us if we're forgotten to enumerate one of these cases. So just using this leads to, I think, much more declarative code and certainly much more readable code than using just a Boolean in this case. Okay, and the last thing that's been great about Scala is the huge ecosystem. So this Java standard library, Scala as well, are both huge, and on top of that, there's many open source libraries, extremely mature libraries in Java and some in Scala as well. That means we don't have to reinvent the wheel, which is also a good thing. So that's all the good things about Scala. There's definitely some bad things, and so this is how we've tried to mitigate some of those bad things. And Scala is complex. It's not necessarily a very approachable language. There's quite a lot of stuff on Stack Overflow about how Scala is complex. And actually, I think it's a bit unfair to say that Scala is complex. I think the real problem is programmers are not particularly familiar with functional programming. It's not really the first thing that you learn when you approach programming. And so if you come from like a Python or a Java background, a lot of Scala feels quite different. It feels very different. And so it's not really a problem if you're working on a project by yourself, right? You can take the time to discover and use whatever you want. But if you're working as part of a team, if you're working on building a team, then this is a real problem. And so we've tried to be quite pragmatic about what we've used. So I think you can think about different aspects of functional programming, sorry, can you all see that? Should I move out of the way? Yeah, the x-axis has values. So basically, you can think of functional features along two axes, 2 dimensions. So basically, I think complexity is how difficult, how much trouble someone who's new to Scala, someone we've maybe just hired, how hard are they going to find reading and reproducing code that uses a particular feature of functional programming. And on the x-axis, we have values. So basically, it's a bit fuzzy, but how much more readable, how much more robust maybe does using this feature make your code? And I'm not saying these are the right answers. I think this is just what our impression has been. But basically things like higher order functions and collections, like the huge collections interface, pretty easy to use, adds a ton of value. Like monadic composition, the fact that basically all of the container types expose map and flat map and filter, and you can use these in full comprehensions. Also not that hard to understand once you've understood it, obviously, but still. Immutability adds a huge amount of value, I think, when you're dealing with a lot of concurrency. Type classes, so extending existing type classes, it's quite easy if you're willing to overlook bits of magic. So with Play framework, if you define like a reads method that's parameterized by the type that you want to read, then you can use Play methods to deserialize JSON into whatever type you want. It's not that hard to understand that if you write a little class and put the magic keyword implicit in front, then suddenly you can use all of Play's methods for deserializing it. Writing your own type classes is quite a lot, maybe more challenging at first. I mean, I think there's a macro now, like an annotation that you can use for type classes. Still, maybe not completely trivial. And then I think higher on the complexity axis, we have things like f-bounded types, path-dependent types, which certainly add value in terms of adding type safety, etc. But they also are maybe not the most approachable feature for someone who's new. And then exotic monads would be things like monads which are not necessarily in the standard library, like the free monad, the state monad, lenses and classes, things that you get from importing Scala Z and cats. So we've basically been drawn a line more or less like this and decided to use everything below it and not things above it, which again is maybe, there's certainly some difficult choices that we had to make there. And I think as a team gets better and as we mature, maybe that line will go upwards a little bit, but we'll see. So to summarize, we've definitely avoided functional libraries. And that's not a value judgment on these libraries. It's just that people who come, like most of the people we've hired are not particularly familiar with functional programming. We've avoided creating our own new type of type classes. So obviously we're extending existing type classes because you have to, and that's useful. We've avoided really defining new implicit conversions because I think they also add quite a lot of overhead, apart from in some cases. We've avoided creating our own domain-specific languages because, to be honest, they often make code much less readable. So yeah, this has basically been our experience. Scala and microservices have really allowed us to manage complexity in a sane way. That's been great, but the barrier to entry for new developers is definitely high, and hiring is obviously quite difficult. I'm basically done, only to say that we are hiring, and Sherlock ML is in private beta, so if anyone is actually interested in trying it out, I know this is an audience of Scala developers. Sherlock ML is mostly for Python, but do get my business card or go on our website, ASI Data Science, and we can give you an invite code. Any questions?
Why you choose Play instead of HTTP?
It's a good question. So the question is, why did we use Play instead of HTTP? So I think HTTP is certainly more lightweight and, in a sense, maybe more appropriate for REST APIs. Play is extremely opinionated, which, if you're working on your own projects, is by yourself is maybe a bad thing. If you're working as part of a team, then being opinionated forces all the code to be kind of consistent. It forces you to use specific libraries, which certainly wouldn't make me feel uneasy if I was working on something by myself. But if it forces consistency across the team, that's definitely a good thing. The real answer to your question is we had to make a choice, and Play seemed like an okay choice at the time.